So now that we've finished talking about these mechanisms, some of which you'll get a lot of experience playing around with, before we get into the details, then let's just kind of talk at a high level about how to evaluate the different approaches that have come out in Java over time. And this is always the case whenever you've got choices between different technical approaches or alternatives. You got to figure out when to use which one, right? And that's a lot of what it means to become an expert at something, knowing the trade-offs between things. So first thing to remember, and we'll talk about this a lot later in the course, Java's concurrency and parallelism mechanisms span multiple layers in a platform's software stack. So if you think about a normal platform like the Java platform or the Android platform, they typically have a bunch of different layers that are baked in there for a whole bunch of different reasons. And choosing the best mechanisms depends on various factors and also depends on where you want to program in this stack. As you might expect, things that are towards the bottom of the stack, which are closer to the hardware, are typically going to be more efficient, but harder to program. And things that move up the stack are typically going to be a lot easier to program once you master the patterns and idioms and so on, but may not be quite as micro-optimized. And so it's that trade-off we talked about before. If you're trying to build performance-sensitive apps, things like a game, like an online gaming system, and you need concurrent processing or parallel processing, you might want to focus on the lower level mechanisms available in Java Util Concurrent, which is a lot of that Java 5 stuff we just talked about, like synchronizers, executor framework, bounded queues, blocking queues, atomics, concurrent collections, et cetera, all the stuff we're going to cover in this class. You may want to use the shared object approaches because they're very efficient. They're harder to program, but they're use the hardware and the system resources very effectively and efficiently and scalably. The good stuff is these mechanisms are very efficient. They're very lightweight in terms of their resource consumption because they're programmed closer to the hardware. The downside is they're a bit tedious and error-prone. So if you're building infrastructure, if you're building the Android platform, or you're building some of the higher layer parts of the Java platform, you're probably going to use these lower level mechanisms to build the infrastructure. But as an application developer, you might shy away from some of this stuff because it does require a fairly sophisticated understanding of concurrency and synchronization. And while you may become a master of those capabilities as a result of taking these classes, the other people you work with on your teams may or may not be that well versed. And so nothing is worse than coming up with this great programming environment and developing all this stuff and then having a team who can't figure out how to use it reliably. It's very frustrating. So these things are great. It's important to know how they work, but you may or may not want to choose them in practice unless you have to build systems where the right answer delivered too late becomes the wrong answer, or systems where every nanosecond counts. And of course, there are systems like that. If you're a gamer, you know how frustrating it is when your games aren't responsive and people don't want to use them. So if you're programming at that lower level, there's a time and a place for this kind of stuff. If you're programming frameworks for higher level use, so if you're someone who's building the Android concurrency frameworks like the async task framework or the handlers messages and runnable framework or the Java executor completion service or executor service framework and so on and so forth, you may be well advised to use Java's concurrency support with respect to message passing. And these would include primarily things like linked blocking queues, array blocking queues, and so on and so forth, synchronous queues. There's a whole pile of message passing based queues that are available in Java out of the box. The benefits of this are they're nicely flexible and decoupled. You as a programmer don't have to think much about synchronization because those things are built into the queues. The queues themselves, the bounded buffers, the thread-safe queues, the concurrent collections, and so on, those have the requisite synchronizers and threading mechanisms built into them. You just have to say, put and take and pass messages between the queues. So that's the good news. The downside is that there could be a bit higher time-space overhead. There's always this trade-off between performance and productivity. And the reason why it could be a little bit more costly to do this from a performance point of view is moving data between threads can incur higher context switching, synchronization, data movement, and cache management overhead. which may or may not matter for what you're doing. But again, if you're trying to like control the inner loop of a nuclear reactor temperature sensor, maybe you want to stay away from some of this stuff. You want to go with something a little lower level. But very few of us are writing code like that anymore, and the hardware is getting pretty fast. So it's a typical time-space trade-off and complexity trade-off. Then the third model here are people who are building apps. I'm using mobile apps because we're using Android here, but it could be anybody building any kind of app. If you're developing apps, if you're an app developer, you probably want to program with these higher level frameworks, things like Java parallel streams, completable futures, RxJava, Kotlin structured concurrency in the form of coroutines, which I think we're going to cover later in the course. So these are higher level frameworks for writing code. They shield you from a lot of the low level details. Your productivity goes through the roof because you're able to focus on your domain intent, your domain requirements, not the nitty-gritty of concurrency and so on. Hopefully your applications will be more robust because these frameworks have been built over time and are well debugged and well optimized and hopefully well documented and easy to use. So it makes humans better. The downside is, as with the message passing model, it could take longer to run, which is always the downside because these things are kind of, abstracting away from the lowest level hardware pieces. And if your model doesn't quite fit, if your programming needs and requirements don't quite fit with the programming models these frameworks provide, you're back to that Procrustean bed problem we talked about before. Now, having said that, most of the time these frameworks are perfectly fine, but it's important to be a full stack developer to understand all the different layers. What is a full stack developer? Full stack developer is a very coveted role because full stack developers are a lot harder to find. They're people who understand the mechanisms and frameworks and patterns and so on at multiple layers in a modern platform. And they can make the right choices at the right point. As a piece of unsolicited advice, thinking about a career, if you want to stay on the technical side of information technology and software development, the more you can differentiate yourself from other people who just happen to know the latest whiz-bang web dev framework, the better off you're going to be. Why is that? Because people who know the whiz-bang latest web dev framework become commoditized because everybody knows the latest whiz-bang web dev framework. And there'll be lots of people who have those skills. And so as a result, whenever there's more supply of something than there is demand, what happens? The price goes down, right? And so you become replaceable. Whereas people who understand the full stack, much harder to find. We don't always need them, by the way, but when we need them, we really need them. And so that leads to a premium in terms of your competitiveness. Anyway, that's a bit far afield from the topic of Java concurrency, but I think it's important to think through the consequences of knowing these different layers.